Welcome to today's tutorial, which is about the most important topic concerning optical modeling, namely finding the right optical constant models. First of all, I will show you in a large section properties of materials related to wave propagation, and then in the end I will recommend appropriate models for the different types of excitations that I will discuss. Let's start taking a closer look at light waves in vacuum first. Basically what I will show you are different areas of the wavelengths, starting here in the range 200 to 300 nanometers. That's called the ultraviolet spectral range, with energies basically above 3 electron volts. Here at around 400 nanometers, we are at 3 electron volts, and there the blue part of the visible spectrum starts. If we increase the light wavelengths, we go through the green part of the spectrum to the red end at 700 nanometers, about 1.7 electron volts. That's called the near-infrared end, or the red end of the visible spectrum. And for longer wavelengths, like 800 or 1000 nanometers, the energy gets smaller and smaller in the range of 1 electron volt. And if we go upwards in wavelengths up to 2500 nanometers, which is still called the near-infrared, then the energy is only half an electron volt. So this is for your orientation, and what I have shown you here are the light wavelengths of light waves in vacuum. Let's take a look at light waves in materials, and I have prepared a little animation where I show you in the top right corner here a light wave in vacuum. Well, it's a slow motion visualization of the light wave. Here you have the position in nanometers, and this is the wave amplitude here. If we stop the wave, maybe we can stop the wave here. We can easily see this is a minimum. The next minimum of the electric field is about 400 nanometers away from that. The same holds for the top. The distance here is 400 nanometers, and this is called the wavelength of this wave. In the bottom section, I show you basically also a light wave, but this is in a material. And the material has a so-called refractive index, N plus IK, where N is the real part and K is the imaginary part. Actually, here I have two sliders, one for N and one for K, which I can use to change the values of these parameters. And we will take a look at different values for N and K and see what this means for the wave propagation. As long as N is about in the order of 1, you can see that the light wave in this material is exactly the same as the light wave in vacuum. Here at the left end, where we see the up and down of the electric field, you can see basically the frequency. The frequency is the same in both cases, in the upper and lower wave. So the wave is basically sent to the right from here with the same frequency in both cases. Let's now change the value of N, the real part of the refractive index. In the first section, I will keep K to be 0, but N will be increased first. Let's go from N to 1.5, roughly 1.5. And what you see here now are two things. Basically, we can stop the wave, and what you see, the wavelength here is not 400 nanometers anymore. It's significantly smaller, and since the wave is still generated with the same frequency here, and the wavelength is smaller, the speed of light is also smaller. You can see that this maximum runs slower than the maxima here. So the wave in this material, n equals 1.5 roughly, is slower than a similar wave started in vacuum. If we go to a value of n of about 2, the wavelength is only 1/2 of the wavelength in vacuum. And if we increase it further on to 3 or 4, which would be something like germanium, then the wave is only 1/4 of the wavelength in vacuum, and also the speed of light is only 1/4, 25%. So the waves in materials with high refractive index n, with high real part, are very slow. Still very fast compared to any motion that you may know from your daily life, but much slower than the comparable wave in vacuum. Okay, let's introduce a value of k different from 0. So if k is a little bit larger, still small, what you see here is the amplitude of the electric field goes down, it decays. This is due to absorption. So the light wave basically is diminished. Light is absorbed. So something converts the energy of the light wave into something else. Usually in the end it will be heat. And so the wave amplitude gets smaller. And this is rapidly happening if k is 0.4, 0.5. Then you have a few oscillations of the wave, and then the amplitude is 0. Let's discuss a case where n is something, the real part is 2, and k is also 2. So they have basically the same order of magnitude. In this case, the absorption is so strong that there is not even one complete oscillation. The electric field decays within 200 nanometers here, so there is no electric field of 400 or 600 nanometers away from the starting point of the wave. This is called metallic behavior. The electric field is only different from 0 in a very shallow range at the surface of the material, but inside the material there is nothing. There is no light. It's absolutely dark. This is extreme in the case of noble metals. Noble metals have K significantly larger than N. So this would be the situation for something like gold or silver. And then you can see here that the light penetrates only maybe half a wavelength or a quarter of a wavelength. So it's not even 100 nanometers where there is electric fields. This is called the skin effect, and which has a lot of consequences, but basically you should remember inside a metal there is no electric field. Okay, this was the behavior of light waves in a medium with different choices for N and K, and this was demonstrated only for one wavelength, for 400 nanometers. In the next section I will show you the complete wavelength behavior for the refractive index, which is of course what we see in spectroscopy. We're looking at many wavelengths at different wavelengths at the same time. Here I show you typical excitation in materials in a huge spectral range. We are going from 10 nanometers here in the deep ultraviolet through 100 nanometers to the blue and to the red part of the visible, and then we go to the near infrared 1000 nanometers, the mid infrared 10,000 nanometers or 10 microns wavelengths, to the far infrared 100 microns wavelengths. So this is a huge spectral range. So I need a logarithmic scale for the wavelength axis here. And I show you two curves in blue, the real part n, and in red the imaginary part K. I start here with vacuum. For this kind of material, the refractive index is, the real part is 1, the imaginary part is 0 everywhere. So this is a vacuum, and now we will take a look at 3 different types of excitation, which are basically the fundamental interactions between light waves and matter. And in the end, I will show you how we can model these 3 types of excitations. The first excitation that I would like to discuss is actually the most important one. It's called interband transition, or electronic interband transition. And if we switch on this type of excitation, you will see that the optical constants show very large structures in the ultraviolet in this case. Here I show you in this example 2 interband transitions, and what you see is that N is affected almost everywhere in the ultraviolet. K is 0 at high energies, and then in this range of the interaction it's different from 0, and then it decays pretty much rapidly to 0 again. Still, the real part has some features which I will discuss in the next section. So let's take a closer look at a single interband transition. And interband transitions occur in almost any material, may it be crystalline or amorphous or molecular systems which have electronic transitions, usually in the ultraviolet, and they are very strong interactions between light and matter. Basically, an interband transition means that you take energy from the light wave by absorption, and you lift up an electron from one band, from one energy band to a next energy band, from a valence band to a conduction band, so to speak. And this means, a very strong absorption for some energies which are high enough to lift up the electrons from one band to the next. Here I show you a single interband transition first, and we can take a closer look. K is very sharp, pronounced, different from 0 here, a sharp peak with a little shoulder, and the consequences for N are, first of all, here in the ultraviolet. We start with at high energies with a refractive index a little bit below 1, and it gets smaller and smaller with increasing wavelengths. That's called normal dispersion. And then inside the excitation, where K is different from 0, we have dysnormal or anormal dispersion, where the refractive index N, the real part, rises very steeply. And then once K goes down to 0 again, we have normal dispersion again, but now starting at the very high level of the real part, N. This normal dispersion now extends to the infrared, where the real part gets almost constant, and I will now vary the strength of the interband transitions, basically the height of the K curve here, with this parameter, and we can see what kind of consequence this will have for the infrared. In the infrared we have this constant, and this constant basically is determined by the strength of the interband transition. If the interband transition is weak, the constant is almost 1. If there is a strong interband transition, we have a very high real part of the refractive index. In the visible, you should notice that due to the normal dispersion, the refractive index on the blue end is usually a little bit higher than on the red end. If we start at a level like this would be typical for glass. The refractive index is on the average about 1.5, but here in the blue it's a little bit higher than in the red. This is a very important feature of the refractive index if you concern the design of lens system, because the focusing effects of lens depends very much on the refractive index. So for blue light, this is different than for red, and so for lens makers, it's very important to know exactly what kind of dispersion you have for this type of glass. Well, if the interband transition gets closer, that means we are looking at the different material with similar interband transition but closer to the visible, then usually the refractive index goes up just because the distance from the visible to the strong excitation in the UV is smaller. And two things happen now. The average refractive index gets higher. Here it's now 2 instead of 1.5. And also the dispersion, that means the difference of the real part of the refractive index and the blue and the red is bigger now. This is now a difference much higher than we had before. And in addition, if you have an interband transition very close to the visible, usually what you notice is that there is already a little bit of absorption in the blue, much stronger than in the red, where still K is almost 0. But usually many materials show some absorption in the blue, which gives them a kind of a yellowish appearance because the blue is missing. It is absorbed when light travels through these materials, which have interband transitions close to the visible. Well, there is no fundamental law that prohibits that an interband transition is located in the middle of the visible. Actually, you need materials like this, which strongly absorb light in the middle of the visible if you want to generate photodetectors for visible light or solar cells that absorb the strong sunlight in the visible and convert the light to electrical energy. In this case, you have to look out for a material which has an interband transition in the middle of the visible. And also it could be in the near infrared. These kind of materials are used to build NIR detectors. Usually also many materials have several interband transitions. In particular, crystalline materials, they usually have many, like 10 or 20 different interband transitions. So I would just show you an example where we have 2 interband transitions, and what you can see here in this case, it's still nicely separated. So we have a peak in K here, another peak in K there. So it's very clear in this example that we have 2 interband transitions. So if we would have to model these optical constants, we would have to use 2 models for 2 interband transitions in this case. But sometimes the interband transitions are not so clearly separated; they are merged, and then sometimes it might be difficult to sort out how many interband transitions you have to introduce in your model to get the right shape of the real and imaginary part here. Good. Let's go on to the next type of excitation. The next fundamental type of excitations that I would like to discuss is called vibrational mode. And here I show you 2 vibrational modes, and this phenomenon is related to the acceleration of charged atoms in a system. Like in a sodium chloride crystal, you have the sodium ions, the chlorine ions, and they are both accelerated in different directions if the electric fields of a light wave arrive at this atom. So you put actually atoms in motion by shining light on this type of material. Since atoms are much heavier than electrons, about 2,000 times heavier, you have to move a huge mass compared to electronic excitations here in the ultraviolet. So usually you need a much slower wavelength, a much larger wavelength to do that, just because the electrons are so, the atoms are so heavy. The exact position of these absorption bands, they actually depend on the masses of the atoms and the forces between the atoms that hold them in their position. So it's a kind of mass and spring system that you try to accelerate very slowly with this typically mid-infrared waves with 10 microns wavelengths on the average. So the peaks that you see here are the resonant peaks of this vibrating system, and the resonance positions are very characteristic usually for the materials, for the masses of the atoms and the forces between them. So mid-infrared light can be used to characterize or identify materials. Sodium chloride has some very nice features that you can very clearly see in the mid-infrared. So mid-infrared spectroscopy is very, very important for chemical analysis, and it's widely used for very elegant contact glass probing of materials with material identification. There's a weak excitation in the near infrared. I will show you a small example here. And this is a multiple excitation of these basic bands. So you take one photon and you generate 2 or 3 of those excitations with one photon. Then you have an excitation in the near infrared, which is also characteristic for the material. And this is widely used for very fast and simple determination of concentrations of all kinds of materials. For example, the concentration of water in textiles or water in food. This is called near-infrared spectroscopy, and it's widely used in, for example, in the food industry to determine the composition of things that we eat. Okay, finally, I will show you the acceleration of free charge carriers by the electric fields of light waves. If you have free charge carriers in the material, that means you have electrical conductivity. You have negative charges, usually electrons, or positively charged holes and doped semiconductors that can freely move in a material. And if you shine light with low frequencies, usually high wavelengths, then you can accelerate those free charge carriers so they start to move in one direction. When the light wave passes through, the electric field reverses its direction. That means the free charges are deaccelerated, they slow down, and then they start to move in the opposite direction once the electric field has changed its direction. This excitation of free charge carriers is a very heavy interaction between light waves and those charges, and it depends very much on the concentration of the free charge carriers. This is in a model. Usually we use the so-called Drude model for that. There's a term called plasma frequency, which is related to the density. And if we start at small densities, a small amount of free charge carriers, let's say like a weakly doped semiconductor, you can see already in the far infrared a very strong effect on the optical constants. Actually, you can see here that we have a transition from this visible and near infrared range, where the real part N is much larger than the imaginary part K, which is almost 0 here. Now if we have charge carriers that can be accelerated by the electric fields of the light waves, we have this transition where K gets larger than N, and this is even enhanced if we go to larger and larger concentrations of the charge carriers. K can be much larger than N, and this is the metallic behavior that I mentioned before when we discussed the light waves in vacuum. So here we have now in the mid-infrared and the far-infrared metallic behavior. Here we have the transition in the near-infrared, and in the visible we still have the so-called dielectric behavior, where N is much larger than K. This transition point moves towards the visible. If we dope more and more, and we have more and more charge carriers, this would be a typical situation for a highly doped semiconductor like a TCO, like a transparent conductive oxide. An example would be ITO, indium tin oxide, which is used as a transparent material in the visible with high conductivity here, made by these free charges that can move, and they have a high concentration. These kind of materials obviously can be used as transparent contact materials for, let's say, solar cells or displays. If you have even more charge carriers, like in gold or in all kinds of metals, then the transition between metallic behavior and dielectric behavior reaches the visible. And in the case of gold, we have this situation that basically for the red light and the green light, we have already metallic behavior, but not yet in the blue. So this is responsible for the characteristic golden color of gold. In the case of silver, we have even more electrons, and the metallic behavior is everywhere in the visible, reaching into the ultraviolet. This, as a consequence, leads to the fact that we have a high reflectivity that goes along with this metallic behavior for every wavelength in the visible. That means silver can be used as a mirror-like material which reflects the complete visible spectrum. So we can use this as an almost colorless, high reflective mirror for visible light. Okay, these were the three basic excitations that I would like to discuss here: interband transitions, vibrational modes, and free charge carrier acceleration. Let's practice what we have learned up to now, and let's take a look at some typical optical constants, and we will find back, hopefully, all the excitations that I discussed. Let's start with to take a look at glass, which is a very important material for for windows, and which also serves for many cases as a nice flat substrate for thin film deposition. The refractive index values that I show here are taken from the database of optical constants. They are not available usually for this huge full spectrum range, but only partial, and we have to identify several parts or several effects that I discussed before. Here I hope you can find back what I discussed. There is an almost constant refractive index of 1.5 in the near infrared, and in the visible we have the weak dispersion that I discussed. The refractive index in the blue is a little bit higher than in the red, and this is obviously due to an interband transition which is somewhere here far in the ultraviolet, not visible in the available data for this material. But what is visible very clearly are vibrational modes, very strong excitations, not so easy to see how many, at least 1, 2, 3 bands here. If you look close, there are typically 4 vibrational modes, which are more or less generated by silicon-oxygen bondings. And these vibrational modes, they are very important for the optical properties of glass in the infrared. In the visible and the near infrared, it looks like K is 0, which is a good approximation in some cases. But if you take a few millimeters of glass and you send light through, you will see that there is absorption, weak absorption, and we can take a closer look. Since we usually use glass with thicknesses of a few millimeters or even more, it makes sense to zoom into this region a little bit, and I do that with a logarithmic scale for n and k. The real part n here is compressed now to almost a straight line with a few wiggles for the vibrational modes. The imaginary part k here now goes through a minimum about 10 to the minus 7 of the real part, so really very, very small absorption in the visible, lowest in the green part here, and rising then towards the near infrared. And in the near infrared, also in the ultraviolet, we see now absorption. It's weak, but on a few millimeters of glass, it's really noticeable. And here you see a broad absorption band, which is due to iron in the glass, iron impurities. And then you see a few steps here, step-like increase of the absorption, and some of these are OH bands, basically water in the glass. And finally, we see the very strong values of K here in the mid-infrared, where we have the vibrational modes that I discussed. Okay, usually if you use materials in a thin film with a few hundred nanometers of thickness, then you would not see these weak absorption processes, and so there it makes sense only to look at strong variation of N and K. Let's take an example of a very transparent material, silicon nitride, where we see very nicely at least one half of a UV interband transition. So K rises very steeply. You can imagine it goes down here, and the corresponding behavior of N is what I discussed before. Strong excitation means strong variation of N, but N also varies when K is 0 in the visible. We still have this normal dispersion, so the real part decays with increasing wavelengths very slowly, causing normal dispersion, much stronger than in glass now, also accompanied by a much higher refractive index in the visible. And here K might not be really 0 as in the case of glass, but since we use silicon nitride usually in thin films, it doesn't really matter, and it's a good approximation to set K to be 0 in the visible in this case. So this would be called a dielectric material. N is significantly different from 0 in the visible. K is 0. Okay, let's take a look at a TCO, a transparent conductive oxide. And I show you two versions. First, an undoped oxide. Those are the dotted lines here for N. Looks very much like the silicon nitride that we discussed before. N would show normal dispersion and then end up in a constant here in the near infrared and mid infrared. K would be a little bit different from 0, where we are close to the interband transition, and then it stays 0 in the undoped version of this material. If we introduce doping, that means the doping atoms release some free charge carriers that can now move and be accelerated by the electric fields of the light wave. Then we have a huge interaction between light and these free charge carriers. The huge interaction leads to the effect that K gets much larger than N. So we find metallic behavior in the mid-infrared and the transition between metallic behavior and dielectric behavior in the near-infrared. And this transition depends on the doping level. Okay, let's take a look at a crystalline semiconductor, gallium phosphide. And here we see at least two sharp interband transitions. And if you look a little bit closer, there's a little shoulder, another interband transition. There's a little shoulder on this side too. So here we need, if we would like to model this shape of N and K, we would need at least 3 interband transition models to be superimposed to get this behavior of K and also the corresponding behavior of N. Okay, this is very typical for crystalline materials, very sharp structures and many. If we go to an oxide or a nitride version of this material, and here I can show you the oxidized version of gallium phosphide, then the situation gets much simpler. So if we look at the oxide version, there's only maybe a single interband transition somewhere here. We have weak dispersion, small, almost boring real part of the refractive index, and K is almost 0 everywhere. So this is a transparent material with a little bit of dispersion, and that's all. So modeling oxides and nitrides is usually very simple. You just use a constant here plus 1 interband transition, and that's it. Very simple. Okay, let's go finally to metals. Let's take a normal metal like chromium. And I told you that N and K in the case of metals have the same order of magnitude here. They are about between 1 and 4. The same size almost everywhere. That means very strong absorption. Remember the skin effect that I discussed in the beginning. And this means that chromium absorbs light very efficiently almost everywhere, ultraviolet, visible, and also near infrared. Let's take a look at gold. Here we find what I discussed before, metallic behavior in the complete infrared regime. Then basically 2 strong interband transitions here in the ultraviolet, close to the visible, and actually in the middle of the visible, or in the blue end, there's an interband transition. So we have, well, not clear, but a little bit dielectric behavior here, but metallic behavior starting with the green and the red part of the visible spectrum. In the case of silver, that I mentioned before, the metallic behavior extends nicely to the ultraviolet, and here around 300 nanometers we have the first interband transition that is really dominant, and but otherwise we see pure metallic-like behavior of this noble metal, silver. Okay, this was the discussion of typical materials. I would like to end this session by recommending optical constant models. So for many simulations, you need a flexible model because materials show some variation. The silicon nitride is not always the same. So we need a model that gives the right shape of N and K, but is a little bit flexible. And optical modeling requires usually that we superimpose several models for interband transitions, for vibrational modes, and for free charge carrier excitation. The situation is not really very complex because I will recommend only a few models. We have seen that in some cases, especially in the infrared, sometimes just a constant is a very good approximation. So, for example, silicon in the mid-infrared is characterized by a refractive index which is almost constant and 3.4. Germanium has a constant of 4 in the mid-infrared, but you may remember that the refractive index, the real part, does not stay constant. If we go to higher energies, it usually rises a little bit, and that sometimes can be described, this normal dispersion can be described in a very simple way by placing an harmonic oscillator somewhere in the ultraviolet. This represents an interband transition which is far away, and we don't care about details. We just want to generate a little bit of dispersion. In that case, you just superimpose a constant and a harmonic oscillator, and you are good. If you see interband transitions which are close to the observed spectral region, then you might need a little bit more details. And there are two models which I explicitly can recommend to be used for interband transitions. The first one is the Taug-Lorentz model for interband transitions in crystalline materials, a very well-known model with 4 parameters and very easy to be applied usually, and very successful for crystalline materials. For amorphous materials, for almost all oxides and nitrides, for sputtered materials, I recommend the so-called OGL interband transition model. This also has 4 parameters, and this generates the right shape of N and K for most materials that I know which have been obtained by sputtering. A very nice model that just reflects the optical properties that we see for those kind of models. Vibrational modes can be described by a few oscillator models. Actually, it's not, for historic reasons, I still have the harmonic oscillator and the so-called Brendel oscillator in my software packages, but I strongly recommend to use the Kim oscillator model for any vibrational mode that you want to describe. This is very successful, very realistic, and also very easy to be applied. For free charge carriers, I have to recommend 2 models. In most cases, you will be successful with a very classical, very simple Drude model, just 2 parameters, the plasma frequency and the damping constant, and the 2 parameters correspond to the mobility and the carrier concentration. So it's also very easy to be applied and very successful for all kinds of metals and lightly doped semiconductors. In the case of heavily doped semiconductors, like the TCO example that I showed before, I have to recommend the extended Drude model, which adds a feature which is missing in the simple Drude model, basically a frequency-dependent damping. This shows up to be important in highly doped semiconductors only. So only in this case you have to use the extended Drude model with 3 more parameters compared to the simple Drude model, but it's also not so difficult to apply this, and especially very successful. Okay, later on in future tutorials I will show you how we can apply these models in order to fit optical constant models to measure data, and but for today I would like to close this introduction to optical constant modeling, and by thanking you for your attention. And so let's wait for future tutorials which show how we can apply these models successfully. Bye bye for today.